Yeah, thanks everyone for joining us today. Like Daniel said, I'll be covering a presentation today just on the basics of GRP for soil nailing and rock bolting in the civil industry. Whoops, having a bit of technical difficulties. Glad we trialed these last week. So what we'll cover today is what ground support we're talking about. So the types of ground support we're talking about are soil nails, which are passive anchors, ground anchors, which can be multi-strand active anchors, and then rock bolts, which can be both passive and active anchors. So this is where we can look at utilising the GRP as an alternative solution, and we'll cover across the testing and requirements for the GRP in these markets. Now, the current standard for corrosion protection into these applications for anchors, the most common is a DCP or double corrosion protection. And that you can see there on the right-hand side, that's showing you double corrosion protection cross-section of a rock bolt. So what you have there on the outside is the grout as your single layer protection, and then you have your sheathing, which is your HDPE, as a second double corrosion protection layer, and then grout again on the inside. And this is your steel bar component, which can be also your multi-strand anchors and the likes. The other options for corrosion protection is galvanizing, which is not your 100-year design life. Your double corrosion protection gives you that. And then other options in the marketplace are doing an epoxy coating, which can give you an extended durability over galvanizing. These are the international standards that for soil nailing and ground anchors that we mostly refer to across the marketplaces. BS 8006 is the British standard for soil nailing. 8081 is for your ground anchors or grouted multi-strand anchors. And then we have Vic Roads for section 683 for soil nail walls. The US Federal Highways Geotechnical Engineering is a good practical application specification. The Euro code within RMS, there are two good specifications there, which is R64 for soil nailing and B114, which is a fairly extensive ground anchor specification. So the Bluey GRP Basics. What is GRP? GRP is referred to as glass fibre reinforced plastic or polymer. You can be noted as GRP, FRP, GFRP. So they're all one and the same, made out of glass fibres. The last one, which is CFRP, is a carbon fibre, generally used for structural strengthening, not for your soil nailing or anchoring market. A lot more expensive in that application. For this purpose, in the presentation, we'll be referring to GRP, which is a continuously threaded bar. How is GRP made? The most common practice for manufacturing GRP is a pultrusion process. And what happens there, you have a fibre bank at the back of the machine here, which has all the fibres, gets pulled through some machines here into a resin bath. And then it comes out the other end, which will be coming out in different shapes, can be made into straight bars, into threaded bars, a whole different forms can be made out of GRP. There are different resin and different fibres that are used depending on the application, but the most common that gets used for the standards are glass fibres, which are 1000 MPa. If you get, like we talked about before, carbon fibres are generally used for structural strengthening in the reinforcement market. And then the critical part is the resins that get used. There are 3 different types of resins that get used to manufacture GRP. Vinyl ester is utilised for permanent applications, and that's we'll cover that further in the presentation about why that's used and the testing that goes with that to justify the design life of the bars. Polyester, which is probably the most common for the mining market because they're a temporary application, so they can be used and then cut through later on. Also in the tunnelling market for your soft eyes and your temporary face support. And then epoxy is more utilised for your self-drilling GRP anchors. So these are different types of bars that get pultruded and the different profiles. The most common up to about probably 5-10 years ago was the straight bars on your right-hand side, these ones here. So you'd pultrude a straight bar and then you'd sand seed it to give you your bond to your concrete. So very common in your reinforcement market. The most recent developments are the ones in the middle, and these are the bars that Bluey produces into the marketplace, which is a fully threaded GRP bar. So you can see there, the fibres are actually wound around the bars to create the thread profile, where traditionally they would have to use a straight bar and then cut a thread into it, which wasn't very strong and didn't give you a lot of load on your nuts and plates. And then on the right, on the left-hand side there, you can just see different applications. You can make mesh out of the bars. You can do grates. You can do a whole heap of things with GRP. So this is just a cross section of the threaded bars. So you can actually see there the longitudinal section showing the threads running right through the, or the fibers, sorry, running right through the threads of the bars. That's giving a lot more strength. You're not breaking any of the threads when you're manufacturing the bars. So it allows you to put a lot more load onto the nuts and plates. So we'll cover across some applications and benefits. Why do we use GRP for the applications of saw nailing and ground anchors? One is durability, 100-year design life. It's got very high tensile and shear strength. Traditionally, people would think that GRP is weak in shear, and probably 10, 15 years ago, it did have a weak shear strength. But with the latest designs and the manufacturing processes, the shear capacity has increased, and I'll cover that across later on. A big advantage is it's non-conductive, so there's no stray currents for corrosion issues for the rail corridors and into power substations. Another big advantage is lightweight. So it's a quarter of the strength weight of steel, but double the strength. So there's less equipment used to handle it on site, less crane movements, less chance of any injuries or risks to the applicators. So where can we use GRP to replace steel? Like we talked about before, we're looking at face and slope stability with saw nailing, ground support, rock bolting within tunneling environments, reinforcement for marine and tunneling and for bridges, and also for permanent and temporary applications. It was usually known as a temporary application for the mining market, but with the international standards, the testing requirements that have come out, there's certainly now permanent applications that the products can be used for and are used for regularly. Like we talked about, the GRP is very safe to install. It's very lightweight. One guy can handle, one person can handle a GRP bar quite easily. You can see on the photo there, you got one person in a cherry picker putting in a 12 meter bar by hand, where if that was a steel bar the same length, that would weigh about 50 kilos. So you need a crane to lift that bar up in place. Like we talked about, the properties of GRP, you've got tensile strength greater than steel. You're looking at a 1000 MPa bar compared to a 500 MPa steel bar. Very high shear strength, and you got a good bond stress for the grout to the greater than steel, and we'll cover that across later on in the presentation. So these are just some comparisons comparing a GRP bar to your steel, from a 25 and 32 millimeter bar, which are our GRP bars that we have into the marketplace. So you can see there we've got a 1000 MPa bar, where traditional steel bar is only 500 MPa. And then if you look down the shear capacities, there's two shear testings there. On a 90-degree shear, which is a knifing shear for a rock bolt application, you can see now that the GRP bar has the same capacity as a steel bar at 170 kilonewtons. In a saw nail application, when you're looking at 50-degree shear, bit of tension into the fibers, you actually increase the shear capacity of the GRP bar. And we'll cover that in the testing aspects a little bit later on. So durability, like we talked about, 100-year design life on the GRP. You're not relying on all the aspects of double corrosion protection to give you your design life. You're not relying on galvanizing and DCP applications where something can go wrong in the application or manufacture of the DCP or installation, to quite simply putting the bar in the hole with the grout to give you your design life. Another big advantage is there's no minimum cover requirements for GRP, so you can actually reduce your hole size of your saw nail or your anchor. As long as you can get the same skin friction out of the smaller size hole, you can save a lot of time and money in those applications. Again, it's a GRP is non-conductive, so eliminates any stray current corrosion for your rail corridors. Can be put into substations, be a lot safer to handle in those environments for the contractors. So what we'll cover here now is all the product testing that gets carried out, what standards are applied for the testing of the manufacture of the GRP, and also for the testing of the GRP once the bar is being produced. The two main standards that are referred to for GRP manufacture and testing are both the American ACI 440 series and the Canadian CSA S807 and S806 for testing. So these cover out, from the manufacturer point of view, what type of resins you need to use, what fibers need to be used as well, and also the minimum criteria for batch testing on the manufacturer side. And then in the testing, it lays out, I'll show you for the next slide, the minimum type of testing that you have to do on the bars to work out what performance you have out of your GRP. No GRP bar are the same, so you can't rely on one person's testing on the GRP bar and apply that as a rule of thumb for all GRP bars. So when the designers and engineers are looking at the design of a sonar wall and utilising a GRP bar, then they have to refer to the testing supplied by the manufacturer for each individual bar to work out the creep rupture, the deformation, the durability performance, and the tensile and bond strength. So they all have different properties, and that's why the testing standards are set in place to make sure that there is an even playing field and you're getting a high quality product. I'll just cover you through some of the critical testings. The creep rupture is one of the main testing that needs to be carried out for a GRP bar. It measures the maximum long-term load that can be applied to a GRP bar. So what we're talking about there is at one point in its life under load, the GRP can rupture. So you've got to work out to the standards where it won't rupture. So in the standard itself, you've got to have a minimum 5 test loads tested. Then they'll pop that out to work out where your rupture point is and where it won't rupture. And you've got to hold that until it ruptures, or for a minimum of 10,000 hours. So 10,000 hours is equivalent to about 13 months of testing. So it's a lot of testing that needs to happen. And we've done this about 4 times on our bars. Every couple of years, we get bars sent up, get them sent over to the University of Sherbrooke in Canada to get them to retest it to make sure that we're getting the same quality out of the fibres, out of the resins, and out of the manufacturing process. So creep deformation, similar sort of testing, but it gets done to 20% and 40% of the capacity of the bar. These are generally the 40% is the maximum working load we apply to the GRP bar, and 20% is probably the most common load capacity on the bar. So what we're doing here is working out what the long-term deformation of the GRP bars are under load. So you can see there in the graph, most of the load or the deformation happens in the first 28 days. And generally it's observed about 5 to 10% of creep observed over the time. Once it gets to load, it will then distribute out and stay stagnant on the deformation. So alkali resistance, this is another critical testing for the GRP. This is testing the durability and retained strength in an alkaline environment. So part of the standard is you have to test in an alkaline bar for 13.5 pH at 60 degrees. And you've got to have it soaked for 3 months. The test standards say you've got to have greater than 80% retention of your UTS in your modulus to be classified as a Class A. Our bars on the marketplace, our GRP 60s, we get about 98% retention of the UTS and 100% retention of the GRP of the modulus. Some bars that we've tested from different suppliers and that we've seen test results on can come back around 40 or 50% capacity or even lower. So this is why you've got to rely on individual tests for each product that's on the marketplace and not take one person's testing and apply that to every single bar. Tensile strength. So this is standard testing that gets done at time of manufacture. It also gets done as local testing when we import the bars. So it's testing the tensile strength, the modulus, and the tensile strain. So like we talked about, just like a steel product, we get batch testing done on every single batch that is produced to make sure that we're getting the same capacity or the minimum standards. And then when the product arrives in the country, we get local NADA testing as well to back up the testing for the local authorities. So shear testing, there's a lot of shear testing that we performed on our bars to justify the performance of the product. So that's equivalent to steel or greater than steel. I'll carry you through those testings now. So the first one was the transfer shear traditional testing in accordance to the ACI and CSA standards to direct double shear to failure. So you can see there, a 20 mil bar has 130 kilonewtons. 25, what we talked about, has 170 kilonewtons in this testing. 2 other shear testing that we've carried out, which is under load, which is the 90-degree shear testing to the German standard, the DIN standard there. We've tested both at 25 mil bars and at 32 mil bars for the application. And you can see there the capacity of both bars is equivalent to a steel bar. Then the other test that we carried out was a 50-degree shear. So this is more for your saw nailing application. When you get your bars activating, you're putting a bit of tension onto your fibres, which increases the shear capacity. And hence you can see the greater shear capacity in your 25 and 32 under this 50-degree shear testing. We'll cover a lot more of this in the coming weeks when we go into a bit more depth about the shear testing and upper test standards. So the bond strength, so this is just testing the pull-out resistance of the GRP bar into a concrete element, and it determines the bond stress between the GRP bar and the grout itself. All the testing that's been carried out shows that the GRP bar has an equal to or greater than a steel bar in this application. So this is just the structural assessment, which comes off the back of all the testing to work out our reduction factors we apply to the GRP for design. And we'll go into a lot more detail in the coming weeks when we do a full design assessment of GRPs for saw nailing. There's two main standards, the BSA 006 and the CSI standards. So the main standards, the main reduction factors are your creep rupture and your durability. So these come out of the tests that we've done previously. So on the creep rupture, we apply a 0.6 reduction factor. So what that means, anything below 60% of load, the GRP bar won't rupture. And then a durability factor, we put 0.65. That's a conservative number based on the standards, but when you add both of those together, we're using a maximum of 40% capacity of the GRP bar. So at that point, we'll never have any creep rupture because we're only at 40% capacity, and there's still a lot more redundancy in the design and in the leftover of the bar. So for a GRP element, we're looking at the design failure being a ductile failure, GRP being a brittle failure. The way we work around that is that the failure mechanism will be between the grout soil interface. So the bar itself won't be into failure, and we'll get a ductile failure by the grout soil interface. The tendon's generally only working at about 10% capacity in a soil nail application. So your bar will pull out of the ground well before you have any failure of your GRP bar. So this is where we're just demonstrating that. So most saw nails, you're looking at pulling out around 150 kilonewtons. The blue line here, I don't know if you can see very well, and the green line is eliminating a steel bar. So you can see there when it gets to close to about 400 MPa, you start to put your steel bar into yield and you'll get your deformation. What happens with the GRP bar, because you've got a lower modulus than a steel bar, you'll start to get elongation in your bar. So you get your signs of failure, you'll get cracking in your shot creep and all those sort of applications. But generally, your saw nail will pull out of your ground well before you get to that application or getting up to your failure of the GRP bar. And that's where we talked about the modulus of the GRP. Being a more flexible bar, you'll see a lot more. If you do have it going up to higher loads, you'll see more deformation in your GRP bar, and you'll see cracking in your shot creep facing and the likes. But most of your deformation generally occurs between your grout soil interface. We've done extensive in-situ testing between a GRP and steel bar side by side to justify this and show designers and authorities this is where the application is happening. And that's what we'll cover off to show you here. So this is a side-by-side test we had carried out. On the left-hand side is showing the steel deformation. So having a higher modulus, you're only getting about 3 mil deformation in your free length. In a GRP, you would expect to get 3 or 4 times that in your deformation in your free length. But when you return back to your datum point of 0, you can see both of them there only having about 0.7 mil of deformation, which is all your grout soil interface. So what we'll cover across now is your GRP approvals. So we've done a lot of work in Australia, working with the local authorities and train networks around Australia to get the product approved with different applications. The first one that helped out a lot was the British standard back in 2011, allowing for the GRP bars to be used as permanent applications in saw nail. So off the back of that, we've done a lot of testing and presentations to the road authorities in Australia to get that updated. So Vic Road was one of the early ones that came on board and it changed the specification back in 2012 to allow for GRP saw nailing for your permanent applications. More recently, Metro Trains in Victoria type approved our GRP bar. You can see the certificate there on the right back in 2017. TMR up in Queensland had approvals and our first projects back in 2014, same as Diptide, which is South Australia. NZTA was first project over there and approvals was back in 2013, which was for the Waterview project, and Skirt was for the rebuild of Christchurch. So we've done a lot of work down there in the earthquake zones to help rebuild the Sumner Road and the likes. And then also the Eurocode 7, which is the European Code for Geotechnical Applications, approves the GRP as permanent applications. And I think that is everything at the moment. So a little bit of a short and sweet brief overview of GRP into the soil knowing market. I guess we can open up the questions. You can either type a question into the chat if you have any, or if you feel like you can email me a question later on my email address, which is down the bottom there. You can take a note of that and give me an email. I can send you out any information that you're looking for, or have a chat about some GRP applications in the future.
Thank you, Greg. That was a very informative and well presented little webinar.